Doom, 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 doom. Remember, statistics is the most powerful magic of all, but it always comes at a price. Today, I have a special thing just for you. I have a real data set. This is not a regression example where I make up the data just for you. I've got a data set that is actually real, where they measured what percentage of the lion's nose is black, and they wanted to see whether that changed by age. Before we look at the data, which I'm telling you, it's real, baby, we can set up our null and our alternative. I know you like the hole in the house. So, for our null hypothesis, what is the statistic we are testing? It's a beta 1. But we aren't just testing whether the nose of the lion changes by age. We're testing specifically whether it gets more black as it gets older. So we're testing whether the slope is specifically, I almost made a mistake right there. Did you see that? I caught myself because I noticed that there was no equal sign. When you say slope greater than 0, because that's what this question is asking for, it has to be in the alternative. The null would then be the less than or equal to. If the slope is positive, that means as the lion gets older, the nose of that lion, that's backwards. That's right for me, but not for you. As it gets older, the nose is increasing in blackness, so it's a positive slope. That's what we're trying to test. So this is a program called RStudio, but that doesn't matter. Just know that I'll take care of you. Here's what our data looks like in picture-wise right there. It looks good. Over here, we've got the percentage of the nose that is black by the age. It's real data, baby. So let's take a look at our residual plots. What do you think of that? Well, there's not a whole lot of data here, but I think it looks pretty good. So now I'm ready to get my output. And let's scoot it over so it fits in the window. Now, there is the table that I am most interested in right here. This tells me about the intercept. Don't really care about that. This right here, that's what I'm interested in. The effective age on the percentage of that nose that is black. So there's my estimate, and there is my standard error. I am going to get my t-score by taking 0.0058591, and I'm going to subtract 0, and then I'm going to divide by 0.0008307. And because I'm a smart guy, I'm going to do that in my head. It's going to be 7.053. Now, you might be saying to yourself, the p-value is right there, but that's not exactly true. Number one, it's in scientific notation. That's terrible. Why would they do it? The point is, that's a doubled p-value, and in this case, it is not a two-sided test. So, I'm going to get that p-value by myself. That t-score is 7.053. My sample size, I need degrees of freedom. Looks like I have 32 data points, so 30 degrees of freedom. I'm going to go to my t-table. I'm going to make this 30 degrees of freedom. I'm going to put in my t-score of 7.053. Maybe p-value is almost basically practically 0 out to 5 decimal places. Now, normally I'd have to double that, which 0 doubled. You know what? It's not doubled because it's a one-sided test. So the whole issue of doubling became stupid when the p-value was 0, because even if you accidentally did double, you'd still get the right value. But in any case, we are going to reject, which tells us lions' noses really do get more black as they get older.